All right. What were we saying? Oh yeah. So capital F is antiderivative. Lowercase f is the original function. So the derivative of the capital F sends you back to the original because you're canceling the antiderivative with a derivative. They kind of undo themselves. Okay, so we'll talk more about that here. So if capital F is an antiderivative of lowercase f on the interval I, then we'll say capital G is an antiderivative hold up 1 second. Double check this. F is G. Okay. Yeah. Sorry, I just, now it makes sense. I wrote this note to myself. I was like, wait a minute. It continues. So this is only true if and only if capital G is of the form G of x, capital G of x, equal to capital F of x plus C. This would be true for all x in the interval I, where C is a constant. G is called the general solution. So we kind of have to add this C here, because if you take a derivative, right? Let's say you take the derivative of capital G, this would turn to lowercase f. This would become 0, right? So basically, general solutions could be in many different forms because you have so many different C's. Basically, you kind of have like a family of solutions. That's essentially where um, eventually, after Cal 2, you get into differential equations and this idea becomes important. Okay, so the operation of finding the general solution is called anti-differentiation, or definite integration. And is denoted by the integral of lowercase f with respect to x, or just dx, is equal to capital F of x plus c. So basically, if you find the antiderivative of lowercase f your original function, you'll get your capital F plus some constant. And you won't know what that constant is without having initial conditions. Okay, so f of x is called lowercase. The integrand dx is the variable of differentiation C is a constant. All right. So this is a symbol we'll use when we're going to take a antiderivative or antiderivative of a function. So the function will be in there with respect to a specific variable, and you're going to get some function. So let me give you the formulas. I need to write a note. So I'm gonna give you some notes and then a bunch of formulas, and then we can begin. It's just it's a lot of foundation on these ideas. I recommend watching the videos as well. But if you're going to calculus 2, you're going to see that Cal 1 was all about derivatives pretty much. Cal 2 is all about antiderivatives. Oh, wait, before we do that, let me write a note first. Integration is the inverse of differentiation. So basically, if you were to integrate, let's say capital F derivative, then they would just cancel. No more derivative, you would just get that function back plus a constant. Also, if you were to do the derivative and have the integral after, you would just be left with the function. So time for formulas. If you integrate or take an antiderivative of 0, you will get a constant. If you integrate k dx, some constant k, then you will get kx plus c, where k is just some real number. Number 3. If you have a k on or some sort of number factor on your function, you could pull that out in front and then do your integration. Number 4, if you have sum and differences of multiple functions or terms, you can integrate them piece by piece. So just do them separately. Do the f and then do the g. Sometimes this is much easier. Just trying to do it all at once might not be simple. This one is the most common, the power rule, but for antiderivatives. So remember when we were doing derivatives, you would subtract one, right? So now you're gonna add one and then divide by that outcome. Integral of cosine x dx is equal to sine x plus c. Integral of sine will be negative cosine plus c. Alrighty. And you can kind of see where we're going with this, right? If you take a derivative of sine, it's going to be cosine, right? So if you undo it, you should get back to sine. But you always have to tack on the constant. You see how it's just backwards? Integral of secant squared is just tangent. Integral of secant tan will be, I believe that's secant. All right. Number 10. Integral of cosecant squared x dx will be equal to negative cotangent. Right, almost done. Integral of cosecant x cotangent x dx will be equal to negative cosecant. I'll put 12 up here. Running out of space. Antiderivative of an exponential, a to the x, dx is equal to 1 over ln a times a to the x plus c. 13 e to the x dx is equal to e to the x plus c. This one should have been obvious, right? Integral of 1 over x dx or integral of x to the negative 1 dx is ln x plus c. Okay. And I think a lot of them are on your formula sheets, but I do want you to see how they are the derivatives in reverse. Does everyone see that?
Yeah.
Okay. All right, so let's do some examples. Find the antiderivative of f of x equal to 2x cubed. So integral of 2x cubed dx is going to be, so let's use our property, right? Pull out the 2, and you keep writing the symbol until you actually take the antiderivative, kind of like when we do limits. So I believe that was rule 3, right? So then do the power rule. So this will become x to the 3 plus 1 over 3 plus 1 plus c. So that is rule 5. So at this point, we've done the antiderivative, so just do some algebra, and you're done. This becomes 2x to the 4th over 4, which is going to be can't forget our constant. So if they ask you to find the antiderivative of a function, set it up like this, put the function in here, use the appropriate rule, maybe pull out a constant or separate it, whatever you got, then do the actual main rule. Any questions on example 1? Does it make sense?
Yes. Especially with the formulas. Be very helpful to look back at those.
Yeah, just use the one I sent you. I think they're in that blue formula page I sent. Find the antiderivative of f of x equal to x squared plus 3. So the antiderivative of x squared plus 3 dx. So what rule should we use here? What do you think? So see how we have two terms, right? Yeah, I think we should do them separately. You're right. So separate them and do two integrals or antiderivatives using rule number 4. So what is this going to turn into? The first one. Yeah, exactly, right? You just do the power rule. 2 plus 1 over 2 plus 1. And then this will become 3x. It's okay to add the c at the very end. Technically, both of them get their own c, but when you add two c's together, you can just rename it c because c is just some constant. It doesn't really matter. Does that make sense? Because we can't solve it unless you have initial conditions. So you could call this the first integral. You could get the x cubed over 3 plus c1. This could be 3x plus c2. And then you can just say, well, you know what? Let c equal to c1 plus c2. So now it's c. But I think it's easier to just think about it this way. Do them separately. Add a single c at the end. Who cares? If you want to get technical, we can get into it if you like, but this is how I want you to think about it. Excuse me. So power rule and then just the constant rule. Any questions on example 1 or 2?
My internet's about to go out right now. You will be posting this on the Remind tonight?
Yeah, yeah, we're almost done. I'll post it as soon as I can.
All right, all right. And I guess I'll see you on Tuesday.
See you Tuesday. Yeah. Let's do another one. Find the general solution of dy dx equal to 3x to the 2/7. Okay. So basically they're just telling you to find the antiderivative, right? Solve for y. In order to get y, I need to do an integration of both sides or antiderivative. Excuse me. Antiderivative of a derivative will just be the function itself. Do this guy, and you'll get 3x to the 2/7 plus 1 over 2/7 plus 1. That looks weird. Okay, so the antiderivative is done. Just got to do fractions. So this will become 3x to the 2/7 plus 1 is going to be what? 9/7, right? So this becomes 9/7. reduce your fraction. I know this step is unnecessary, but there it is. I'm sure y'all know how to do fractions. But just in case, if you have any questions how we got here. All right, cool. Move on then. Second. All right, so in order to do this one, we're going to need this old school rule because we can't integrate the fourth root of x, but we can integrate x to the 1/4, right? So that's just a simple power rule. So 1/4 plus 1 over 1/4 plus 1 plus your c. This simply becomes x to the 5 fourths over 5/4, which is simply 4/5 x to the 5/4. Just using your power rule. Okay. Any questions on example 4? Okay. Let's do a different type. Notice how here we have thetas instead of x's. Same stuff. Just theta, secant squared theta, d theta. So everything will be with respect to theta. So first thing we should do is separate the integrals. So this will simply be a power rule, right? This will be formula. This should be what? What is the antiderivative of secant squared?
Tangent.
Yeah, it's gonna be tangent, right? So this is power rule, this is tangent. Any questions on 5? All right, let's do a couple more and we'll call it a night. 2 more examples. Excuse me. All right. So here we have a trig function and an exponential, and they both have numbers in front. So we should separate them, pull out the numbers, apply the formulas. So here we go. Separate this guy. Separate this thing. Pull out your 3. Now apply the formula to the thing inside, the integrand. Antiderivative of sine should be negative cosine, right? Antiderivative of e to the x will be itself. And add your c. And now these numbers are just waiting for you. The minus that was here will be waiting for you too with the 7. So now we're done. Negative 3 cosine x minus 7 e to the x plus your constant. Any questions on 6? All right. Find the particular solution of the differential equation. So we're not going to do this very often in Cal 2 or Cal 1. This will be what differential equations will be about, just in a larger scale. This type of question. So when you have an equation full of derivatives and you want to find the original function, you're going to have to use various techniques, and you will need an initial condition. So here's the function. All right. So in order to solve for f, we got to take the antiderivative. Once you do so, you're going to find a constant c. So use this initial condition to solve for c. So right here, you should see that this will be 1 plus 1 over 1 plus 1 plus your constant c. So f of x is equal to 4x squared over 2, which is 2x squared. Oops, forgot my c. Can't do that. My professors would mark the whole thing wrong if I forgot the c. Different generation, I think. Okay. 2x squared plus c is your f. So use that, this point. So remember, f of 0 equal to 7 is the same as saying 0 comma 7, right? Y'all remember your college algebra? It's basic function stuff. So just plug it in. Basically, it's saying that f of 0 is equal to 7. So that means that c has to be 7, right? So the general solution is f of x equal to 2x squared plus 7. So this is what they want. And in real life, initial conditions could be like initial position, initial temperature, initial, I don't know, mass or something, etc. But when you start doing like a lot of more complex physics problems, I don't know if you have you guys taken physics yet? You know how they try to ignore air resistance or ignore friction, whatever. Yeah, when you don't ignore it, the math gets gross. Then you start getting differential equations popping up everywhere because real life is complex. And then you got to solve them. So solving for your force would be a complex derivative, like way harder than this, right? And you'll have different conditions to help you find your constants. So eventually this becomes useful in higher level physics and uh, you know, engineering, etc. I mean, if you don't like physics or engineering, I guess it's fine. It's not everybody's cup of tea. Let me take roll and we'll call it a night. I think that's all. That's enough.